This final video on stacks will focus on some more interesting applications of this data structure. First, we will look at the problem of balancing parentheses and other delimiters. This is a sequence of several delimiters. This sequence is considered balanced because every opening delimiter of a given type matches with a closing delimiter of the same type, and I'm able to draw these lines connecting each opening delimiter to its closing delimiter without any of the lines crossing. This is not true in this next example, where I have an opening curly brace, an opening parenthesis, and then a closing curly brace, and then a closing parenthesis, and then an opening square bracket and a closing square bracket. Now, if I'm exclusively drawing lines on the bottom, I can connect the opening and closing curly braces, but now I can't draw a line from the opening parentheses that connects to the other one on the bottom side without crossing this line there. So there's a cross. So because those do not match properly, this is not considered a balanced string of delimiters. The need to verify matched delimiters often comes up when checking the syntax of a program, such as this one. This program actually takes a string of input and then uses a stack to determine if that string has balanced delimiters. So we have a stack of characters, and the particular implementation we use is an array stack, though any stack implementation could be used here. We then loop through all the characters one by one, save them into a variable C, and then apply a switch case structure to handle different characters in different ways. There are three broad classes of characters. We have characters that are opening delimiters, and for all of these, we push that character onto our stack. The next case, or set of cases, is for closing delimiters. If we have any of the closing delimiters, we first must check that the stack is not empty. If the stack is empty, we will return false, because this implies that we had a closing delimiter appearing before its corresponding opening delimiter. But being non-empty is not enough. We must also assure that the delimiters match. So if the delimiters do not match, we will also fail immediately with a result of false. And so what does this delimiters match method do? It takes a character from the stack by popping off the top value, and it takes C, which is going to be one of these three closing delimiters. Remember that we just assigned C here, so it is the most recently read character from the string. It must be one of these three closing delimiters. So what we have here is an opening delimiter of some sort and a closing delimiter of some sort. Those are the only possible inputs that could be sent to this method. But do those delimiters match? That is what's being checked here. So the delimiters are considered a match if the right opening is paired with the right closing. So either opening and closing parentheses, curly braces, or square brackets. In any of those cases, this method will return true. However, if open were a parenthesis and close were a curly brace, that would not satisfy this Boolean expression, and we would get a result of false here, which when negated is true, causing the overall result from the method to be false. So we have to make sure that the stack is neither empty nor has non-matching delimiters in order to reach this break statement, which simply continues looping through the characters. The last case is for all other characters, because if we're processing the text of a program, then there's going to be lots of characters in the program text that are not delimiters, and those can simply be ignored. Now there is one caveat here that is not being handled that I'll return to in a moment. However, let's assume we're in the simple case and that we finish this loop, meaning that we have looped through all characters in the string. So that means we can get to the final result, and all we have to check for that final result is that our stack is now empty. If the stack were not empty at this point, it would mean that there remained some opening delimiters whose corresponding closing delimiter never occurred in the string. So we are only correct with a matching string if the stack is now empty at this point. We can test this method out with the code above. This is a main method that launches some test cases. These are the specific strings we will test, and this little helper method here will output either balanced or not balanced before the input to show us what's happening. So let me go ahead and run this to get these results. And what we see is that this string is balanced, this one is not, this one is balanced, and these ones are not. So this was what we had earlier on our whiteboard, so it's clear that this is balanced. This one is not balanced because we have an opening parenthesis immediately followed by a closing curly brace, so those do not match. Here we have a small but simple Java program which consists of curly braces for defining the bounds of the class and the main method. We also have parentheses for the parameter list of the main method and square brackets for the string array of arguments, as well as parentheses here for the println method call. The next input is that exact same program, but we forgot the closing curly brace at the end. And so we detected that as not balanced, and hence the result here. This final input is only closing delimiters. So if we encounter closing delimiters, but we never had any corresponding opening delimiters, that would also be a fail case. I'm going to walk through the behavior of the stack during execution of this algorithm for one of the successful inputs. If we're processing this string from left to right, then at the line where we are pushing the character onto the stack, which is specifically here, then the character we're pushing is this opening curly brace. So we have a stack and we have this curly brace on it. As we loop through again, this will be the next character C, that opening parenthesis. So at this point, we have a curly brace and an opening parenthesis on our stack. Then the next value of our variable C is this closing parenthesis. So when that is read in here, we go to this case because the closing parenthesis is right there. And so that means that the stack is not empty, so this is not true. So that means we're going to have to check whether the delimiters match. If we pop off the top character from the stack, then we'll be popping off this opening parenthesis. So the call to delimiters match is comparing this opening parenthesis to that closing parenthesis, and when they are compared, they do in fact match. We've now removed that from the stack, so the stack just consists of the curly brace at that point. Next, we encounter the opening square bracket, so that gets added to the stack. And then we have another parenthesis. And then at the next step, we encounter the closing parenthesis. That puts us once again into this case here. So we will compare this opening parenthesis to that closing. Because we've popped it off, the stack now looks like this. The next step, we compare this opening square bracket to that closing square bracket. We've popped it off. All we have left is that curly brace there. And then finally, we compare that opening curly brace to that closing curly brace when we pop it off. And at this point, the stack is empty, which is why we'll get a true result if we return whether or not openings dot is empty. So if this final closing curly brace had been missing, then the stack would not have been empty, and the result for openings dot is empty would have been false, and we would have returned a result of false. If instead this opening curly brace had been missing, then that means it would have been missing from the stack in all of these steps here, and there would have been nothing to compare against this closing curly brace when it was encountered. That would cause a false result to occur inside the loop at this point when we check if the stack is empty. Also, if any of the pairs of delimiters had not matched, then that would cause this check to fail, also causing a false result early in the execution of the program. The last thing I'll say about this algorithm is that although it can verify whether or not the delimiters in a string are balanced, it wouldn't necessarily work on any Java program, because in Java programs, we can put delimiters inside of single quotes, as we do here. If I were to feed this specific Java program into itself, then it would fail because it would not realize that this opening parenthesis does not need to match up with this one or any other parenthesis in the program. To correctly handle this would require some special cases dealing for whether or not we are currently processing a part of the input that is in between single quotes or even double quotes. Stacks are also useful at processing mathematical expressions, but in order to explain this, I will need to discuss some different types of expressions. Most of us are familiar with infix expressions like 5 plus 7 and the more complicated 3 times quantity 6 minus 2. These are called infix expressions because the operator is in between its two operands. We also have some familiarity with prefix expressions because this is how most function and method calls look, such as f of x or math.min 3 and 1. Of course, these are only prefix in the sense that the function name comes before a list of operands which are in parentheses and separated by commas. But you can also have a prefix expression that looks like the following: plus 5, 7, and multiply 3 minus 6, 2. So this prefix expression is equivalent to this infix expression above, and this prefix expression is equivalent to this infix expression. And so we are not used to seeing operators in a prefix position. We see function names and method names that way all the time, but usually not operators. These expressions are also different from the ones above in that we don't have parentheses or commas indicating which operands belong to which operator. But we can actually get away with this without any problem as long as the number of operands for each operator is fixed and known. The number of operands that an operator has is known as its arity. Because plus and multiplication and subtraction all have an arity of 2, we don't need any parentheses here. We simply know that for this minus, the two operands that follow are associated with it. And for this multiplication, we have an operand, and then we have the beginning of a new expression, but we know that whatever the result of that expression is will be the second operand to the operator multiplication. This is actually an improvement over infix notation, which must have these parentheses to distinguish this expression from one in which we would multiply 3 by 6 first. That leaves us with the final type of expression known as postfix. Postfix is similar to prefix, except the operators appear after the operands, as in 5, 7 plus, and 3, 6, 2 minus multiply. The major benefit of this type of expression is that it is very easy for computers to evaluate using a stack. In addition, there exist algorithms for converting between expressions of any one of these types to any other, but I will not be showing all of those. I will only show you the algorithm for taking a postfix expression and computing its result. First, an example. Our algorithm will function by processing this sequence from left to right, and our stack will hold operands. So if I'm going from left to right here, I would encounter the 3 and put it into my stack. And when I encounter the 6, I add it on top. And when I encounter the 2, I put it on top. At this point, I encounter my first operator. Whenever I encounter an operator, I will pop 2 elements off of the stack, because that is the arity of these operators, apply the operation to those 2 elements, and then push the result back onto the stack. Now, the order of a minus operation is very important. What I'm computing here is 6 minus 2. So the 2 comes off first, but it will be the second operand in this operation. 6 comes off here, so I'm computing 6 minus 2. That equals 4. 4 is what goes back on the stack, so I will erase all of this and be left with 4 on the stack. At this point, I've processed these elements of the input. The next thing I encounter is multiplication. So I will pop off a 4 and pop off a 3, do a multiplication to get a result of 12. Now granted here, the order isn't significant with multiplication, but I have to have some rule for how I'm going to apply these operations. So these elements were popped off, the stack is empty momentarily, but then I put 12 back on. And I will continue processing the input. The next thing I encounter is a 7. So 7 goes on top, then a 5. Then I encounter a subtraction, so I will put 5 here, put minus between it and the 7, which I also take off. That result is 2. I've removed these elements from the stack, so I'll put the 2 back on top. And then I encounter a slash for division, so I will have 2 and 12. So 12 divided by 2, that equals 6. And at the end of all of this, I put that on the stack. And as long as the input is a properly formed postfix expression, this algorithm will always terminate with exactly 1 value left on the stack, which is the answer. And so that is it. The answer is 6. And now a quick look at the Java code that would perform that sequence of operations. So the method in question is evaluate postfix, which takes as input a string like what we saw previously. And importantly, every operand and operator needs to be separated from the things that neighbor it by white space. because we're going to process everything using a scanner, which is able to process string tokens. So we set up a stack of double values. These are our numbers. And we happen to use an array stack, although any stack will do. We're going to process the string using a scanner, and we loop as long as there is a next token inside of this scanner. And we get the next token there. And so this token could either be a number, meaning an operand, or it could be an operator. And we're assuming we only have well-formed expressions, so the operator can only be one of four things. In fact, we have a case for plus, minus, multiplication, and division, but we're going to treat them all the same. In all of these cases, what we will do is assume we already have elements on the stack. Because if it is a properly formatted postfix expression, we have to have encountered some operands before we ever encounter operators. So we pop off the top of the stack. That will be the right-hand side of our mathematical expression, so we pop. And then we pop another element off the stack, and that will be the left-hand side of the operation. And then the token is one of these four values. So we have a method, perform operation, which performs whatever that mathematical operation is to the left-hand side and the right-hand side. And this helper method is declared down here. You can see that it has another switch case. There's a case for each operator, and they all look very similar. We simply have the left-hand side followed by the operator, and then the right-hand side, and we return that value. And since we're returning it, that will exit the method. We don't have to have an explicit break from the switch case statement. And if we're only ever calling this method using our code above, we shouldn't ever have any string inputs to the switch other than those four operators, but we have an illegal argument exception just in case that somehow happens. After the result is returned by perform operation, we save it in this variable result, which we push back on the stack. So as in the example I showed previously, we pop off two elements, perform the operation, and put the result back on the stack. We break out of that case. The only other case, besides these four special operators, is some sort of number. So whatever we have must be a numeric operand. We will therefore parse that string token into its double representation and push that onto the stack. And that is all you need, that loop right there. Afterward, for the sake of tidiness, we close the scanner, and if it was a properly formed postfixed expression, there will be exactly one element left on the stack, and we pop and return that to get our result. And if we scroll up, we see some example postfixed expressions being sent to this check method, which indicates that the result of the expression evaluates to whatever evaluate postfix returns. And so if I call this, we'll see some examples. And sure enough, all of these results check out. This is the result we had previously in our example. This is the first part of that expression. And there's a simpler one. And then here is another complex expression whose correctness you can verify on your own.